All right, this is the video key for the Chem 102 hourly exam, number 1. I'm going to go through this exam and I'm going to explain all of the problems for you, and hopefully that will help you both study for the final exam and also will give you an idea if you want to do a regrade. Now, on my exams, you always need to remember to write your name on every page, and also the first thing that you should do when you turn the exam over is pledge the exam. Bruce Banner is taking my first exam. He always takes my first exams. All right, let's turn this over. There's Bruce Banner. All right, question number 1. This should look really familiar to you. This was based on a homework question, and I think it was asking you about ethanol, if I remember correctly, and instead we are asking about methanol. The pressure exerted by a column of liquid is equal to the product of the height of the column times the gravitational constant times the density of the liquid. I even gave that to you, so you didn't have to derive it. How high a column of methanol, density here, would be supported by a pressure that supports a 713 millimeter column of mercury with the density given as well. All right, so we're told that the pressure is going to be the same in both cases. The pressure of the column of mercury is the same as the pressure on the column of methanol. All right, so P mercury equals P methanol. Now notice I'm going to be going through these problems slower than you probably did them on the exam, just because I'm trying to explain them thoroughly to you in case you didn't understand them. All right, so these pressures are the same. So that follows that we could set up G, H, and D to be the same. All right, so I've got gravity times the height of the mercury column times the density of mercury should equal gravity times the height of the methanol column times the density of methanol. Now, something that you'll notice here, gravity is on both sides, the acceleration due to gravity, so we can just cancel those out. All right, and here's what I'm left with. Now, what I'm looking for is the height of that methanol column right here. It's what I'm trying to find. So let's see if we can rearrange this now. H met would equal the height of the mercury column times the density of mercury over the density of methanol. All right, easy enough. Height of mercury, 713 millimeters, times the density of mercury, 13.6 grams per mil, divided by the density of methanol, 0.79 grams per mil. Grams per mil cancels out, leaving us with a unit of length, which is good because that's what we're looking for. 12300 millimeters is what I get. Now, I don't want to really leave it in this form. If I don't put a period here at the end, then those zeros are not significant, but it can be a little bit ambiguous, as we've seen in other places in the textbook. It's really better to convert this unit to meters. You can go 1, 2, 3 and write 12.3 meters, or you could write 1.2, I think somebody wrote this would be fine, 1.23 times 10 to the 4th millimeters. That's kind of strange, but you could do it, that would be fine, as long as you had some iteration of this. I give you full credit for that particular problem. All right, on to number 2. Define STP conditions. That's 273 K or 0 degrees Celsius, either one is fine, and 1 atmosphere. What is the molar volume of an ideal gas at STP? If you'll recall, 22.4 liters. So you got 1 point for this and 1 point for this. All right, then you're given a question about some gas on the surface of Mars. The average temperature on the surface of Mars is negative 55 degrees Celsius. All right, so I'm going to go and write that down. T equals negative 55 degrees Celsius, which also equals 218 Kelvin. All right, and the pressure is 5.92 times 10 to the negative 3rd atmospheres. 5.92, 10 to the negative 3rd atmospheres. We want to know what is the volume, the molar volume? So the volume of 1 mole of an ideal gas under these circumstances. All right, well, we can take PV equals nRT. We can rearrange to find volume. V equals nRT over P. We're dealing with 1 mole times R, 0.8206 liters atmospheres over mole Kelvin, times temperature, 218 Kelvin, divided by pressure, 5.92 times 10 to the negative third, 8 cm. Let's just make sure everything cancels. Moles cancel, Kelvin cancels, atmosphere cancels, I'm left with liters. Liters is what I want. Great. As far as significant figures go, you've got 3 sig figs here, 3 sig figs here. This is a constant, so it doesn't count. This, I put 1 decimal place there, but really if it's molar volume, 1 mole defined, we don't really count that for sig figs either. So our answer should have 3 significant figures. 3.02 times 10 to the third liters. All right. There's that one. Sweet. Let's look at number 3. There's Bruce Banner. Now just remember I said in the exam you had to have your name on every physical page, not necessarily front and back. I'm just doing this so that way if anybody prints out the key, it's easy for them to know that this is the key and not anything else. Okay. All right, so we've got a 4-liter scuba tank filled with a special breathing mixture called trimix, and the amounts of gases are given here. The final pressure is 2,800 pounds per square inch, and we're given the conversion here between psi and atmospheres. We are asked what are the partial pressures of each gas in the tank in units of ATM. So there's a couple ways that you could solve this, but here's what I'm going to do. I'm going to take 280 psi, and I'm going to convert that to atmospheres. 1 psi is equal to 0.0681 atmospheres. So I get 190.68 atmospheres. I'm going to call this 191. There are really only 2 sig figs here. I'm putting that notation, that little bar above the 1 to let me know that that's not really significant. All right. About 191 atmospheres. Okay, so to find my partial pressure of oxygen, I'm going to take 191 atmospheres, and I'm going to multiply that by 0.21 for that 21%. And I get that 40 atmospheres, 40 with that decimal point there to make that significant, that's contributed by the oxygen. For the helium, again, same idea. Atmospheres times 50% helium gives me 96 atmospheres. For nitrogen, ATM, oopies, times 0.29 gives me 55 atmospheres. Cool. All right. While diving with this mixture, I notice a hole. Oh, by the way, this is 3 points, so 1 point each. While diving with this mixture, I notice a hole in my regulator hose. Which gas will effuse at the fastest rate out of these 3, oxygen, helium, and nitrogen, and which will effuse at the slowest rate? Well, the fastest one is helium. You don't have to say why, but helium's got the smallest molar mass, so it makes sense that it's fastest. The slowest is oxygen. It's got the highest molar mass out of all of those. So you got 1 point for helium, and you got 2 points for oxygen, because I thought, maybe somebody might pick nitrogen instead of oxygen. They'd be more likely to do that. Okay. All right, so here we go. So I am diving at 99 feet. I'm under about 3 atmospheres of pressure due to the water, and I see a great white shark coming towards me. Oh, noes. So I drop my weights, and I rocket to the surface, and I'm so freaked out that I'm holding my breath. All right, I've got a full, about 4 liters. Your lungs have a capacity, I think, of about 3.5 to upwards of 6, I think, for some people. But let's say I've got a lung capacity of 4 liters, and I have a full lung full of air here. My lungs at the start of ascent had 4 liters in them. The pressure in my lungs was due to the water and to Earth's atmosphere. And the barometric pressure that day was 1 atmosphere. So the total pressure that my lungs are experiencing, so P total of the gas in my lungs is the 3 atmospheres of water plus the 1 atmosphere, 1.0. So I total at the very bottom, when I first see the shark, the gas in my lungs is under a pressure of 4 atmospheres. Now all of a sudden I surface just as fast as I can, very bad idea, and I need to know what the new volume of my lungs is when I reach the surface. I can use Boyle's law to calculate this. P1V1 equals P2V2. V2, my new pressure, or my new volume in my lungs, is equal to my initial pressure that I experienced, so 4, times my initial volume over my final pressure. All right, my initial pressure, like we just calculated, was 4 atmospheres. My initial volume of my lungs was 4 liters. The final pressure that I experience when I surface out of the ocean is just due to the barometric pressure, 1 atmosphere. So the volume of my lungs is now 16 liters. Not good. All right. So let's move on to the last part of this problem. I'm in the hospital now, clearly, because I have lungs that have burst out of my chest. Wouldn't really do that, but you would be desperately injured. So I'm in the hospital. I'm getting life-saving treatment, not just for the air embolism from my, lungs, but also because I've got the bends, right? Remember Henry's law that we talked about recently? That's also been a problem when I surface so fast. And when I'm there, my friends that took me to the hospital left my scuba tanks that were not used, my full scuba tanks, are left to sit in the back of my minivan. Uh-oh. The temperature outside is going over 100 degrees Fahrenheit. What is the danger in leaving these tanks in the car? All right, explaining this on a molecular level, referencing one of the gas laws. All right, the gas law you want to reference is Charles's law. An increase in temperature leads to an increase in volume. So the gas can expand in the heat, and the tanks are at risk of exploding. Hopefully you just have a cap pop off before the thing would blow, but either way, not a very nice thing to have happen.